is, I think, one of the most exciting steps in the design flow for me anyway. It's the correct the image part. These are examples of products that Synopsys sells, and these are just some pretty pictures again of chip layout and some of the layers. So let's go into this correct the image step. Over time, the chips have been getting smaller and smaller. So remember how I told you that there's a stencil, a photomask, if you like, a stencil, and we shine light through it. So as that photomask has been getting smaller and smaller and smaller over time, because the wires and the transistors are getting smaller and smaller, at some point, the wavelength of light that goes through that stencil is too big. And the crossover point came right around in here in, say 1997-ish or so. And this presents a really big problem because if the light is bigger than the stuff you're trying to print on that wafer, you've got some really hard things to do. One of the things you could do, obviously, is, well, let's just use smaller light. Why don't we go to X-rays, which are very, very small? And certainly that's a solution. The problem is it is so expensive to switch over to X-ray machines as opposed to regular light ones that the cost is just completely prohibitive. And I keep saying how we need to keep the cost down. So I don't think the world would be ready to switch to X-rays at this point. It's just too expensive. So guess who solves this problem? EDA to the rescue. And I'm going to show you how we do this. I love this part. All right. So here is your chip design. And let's say that you're going to do this at 250 nanometers, which is pretty old technology by now. It's still pretty small, but this is what we used to do, in the mid-90s. Let's say this is your transistor that you're trying to print. So you have a nice transistor there. You create that mask, that stencil, to look just like it, and you shine the light through, and the light prints on the wafer pretty close. The light's kind of bouncing around a little bit in the corners, but that's not a big deal. And remember, this is the photolithography where the light is going to, imprint or make that chemical hard. And so you're going to get the right shape. And life is good. However, when we get to 180 nanometers, which is a little bit smaller, we have the design. We create the mask, looks just like the design. But the problem is now the light's getting too big to fit through, and it's not all getting there. So we end up, instead of a nice sharp little transistor there, we end up with a puddle of blah. And that transistor is totally not going to work. So we, in the EDA industry, some brilliant scientists who know how light works, said, you know what? Instead of drawing a mask that looks like that, if we create a mask that looks like this, maybe we can trick the light and bend it around and bounce it in different ways so that when the light comes out, it's going to actually give me what I want. This step is called OPC, which is officially optical proximity correction. And these little extra rectangles that get added on, they're officially called Mickey Mouse ears. But you can see the technology now in just a software tool has been able to say that light's too big, trick it, now I can get exactly what I want, and I don't have to go buy an entire new manufacturing process that includes X-rays or some exotic thing like that. Okay, so life is good again for a few more years. Now we get even smaller, and now we're at 90 nanometer and below. And this is where we are today in most chip technology. So we have the shape we want of the transistor, we do the mask, and guess what? No light goes through whatsoever. We're so small, the light's just bouncing right off, and that's a real bummer. So we invented, I didn't, but the smart engineers in EDA invented a way to go to the mask, and they actually etch it away a little bit. They reshape it so that the light goes through at different angles. And when the light goes through at different angles, now it's able to come out and actually print something. And this step is called PSM, or phase shift mask. And you think that looks okay, but actually this is not going to work. That transistor, or whatever you're trying to print, is still pretty screwed up. So the next thing you do is go ahead, put a little OPC back in there, just like we did over here, where you add some Mickey Mouse ears into that mask, and guess what? Out comes your transistor just the way you wanted it. So it's absolutely phenomenal. Again, the way we've saved the industry so much money is by doing this in a tool, a software tool, with just programming and intellectual property and good ideas, rather than saying you have to go buy a whole new machine or a whole new factory. Interestingly enough, if you want to build a factory that builds computer chips, you're looking at $2 to $3 billion investment. So we're talking big, big bucks. Again, EDA to the rescue. And this is, again, the diagram of a massive file that's going to go off to the manufacturer to create your chip.